Alrighty, that brings us to page 2 of our chapter 2 review, which is going to cover problems 7 through 11. Number 7, a ball is thrown up into the air with a velocity of 96 feet per second from a height of 112 feet. The height of the ball for t greater than or equal to 0 is given by that function. Okay. Now it makes sense. If t is equal to 0, I plug 0 in, the ball is 112 feet above the earth, the ground, whatever. Okay. So let's look at part A, the maximum height that the ball attains. So I already put that here on the scratch paper so I don't forget. Here's my function that I'm working with. I'm looking for the maximum height that the ball attains. And you should be able to do this with and without a calculator. With a calculator, it's super simple. Without a calculator, it's pretty easy too. Alright? So, I'm going to do both ways, but I'm going to show you without the calculator first. What I know about this function without a calculator is that this is a quadratic function, so the shape of its graph is parabolic. And the other thing I know is that since the coefficient, or the leading coefficient, is negatively valued, that means the parabola is going to open down. So I've got this ball that I toss up in the air, and it goes, up, 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 and stops for a split second, and then starts heading back down toward the earth. So that's essentially what my graph is going to look like. Now, if I remember from algebra, we had this simple little formula that we could use for quadratics to find the x-coordinate of the vertex of a parabola. That formula was x is equal to negative b over 2a, where a is the leading coefficient, b is the coefficient of the linear term, and c is a constant, right? And in this formula we don't need the c, but if you remember that from algebra, your ABCs, you could plug things into formulas pretty easily with quadratics. So, in this case, the x-coordinate of the vertex of this parabola is, you can call it t if you want to, right? And the only reason I'm saying that is because our variable is in terms of time. So let's see what happens. We've got negative b over 2 times a. Negative divided by a negative gives us a positive. We get 3. So this doesn't tell me what the maximum height of the ball is. It tells me the time at which it attains the maximum height. Why is that important? Because if I know what time the ball attains the maximum height, then I can plug that time into my function to find that maximum height. So what I know is that h of 3 is going to give me that maximum height that I'm looking for. 3 squared is 9. And if I clean that up, I get 256 feet. Okay, so again, I'm going to show you this on the calculator. I'm just going to validate what I'm doing using the calculator. That way, if it's a non-calculator problem and you end up with one of these on your test, you can do it. And if it's a problem where you get to use your calculator, you can do it. Okay? So, pretty simple to do. Not a whole heck of a lot of math or manipulation or anything like that. Pretty cut and dry. In part B, we want to find the average velocity between t equals 0 and 7. Well, that's really simple too, right? Because we know that average velocity is equal to f of b minus f of a over b minus a, where a and b are the endpoints of your interval. So that means, well, I should use h here, but h of 7 minus h of 0 over 7 minus 0. Well, if I compute h of 7, that's going to give me negative 16. 7 squared is 49, plus 96 times 7, plus 112 is 0. H of 7 is 0. And h of 0, well, that's easy. If I plug 0 into this function, I get 112. So the average velocity is equal to 0 minus 112 over 7. And that's going to give me negative 16 feet per second. Again, pretty simple. Not a whole heck of a lot to that. Now, they want us to find the velocity at t equals to 3. Well, a few minutes ago, we found that the x, or the t coordinate of this parabola, of the vertex, was 3. And if I draw a little tangent line at t equals to 3, which is the top of that parabola, the slope of my tangent line is 0. What that means is my velocity is 0, right? The velocity is the slope of the tangent line. Now what if I had to demonstrate this mathematically? Yikes. That means I have to find the limit as h approaches 0 of h of 3 plus h minus h of 3 all over h. Now don't let the function's called h, right? Let's remember, here it is, h of t. So, if that bothers you, it shouldn't. You could change those to f's if you want to. It's no big deal, it's just notation. This h, though, and this h is not the same as those h's. So I just want to make that clear. You can't just start canceling h's out. They're not the same. This is the function h evaluated at 3 plus h. So what is h of 3 plus h? Well, it's negative 16 times 3 plus h squared plus 96 times 3 plus h plus 112. And expanding this part here, I'm going to have 9 plus 6h plus h squared. 96 times 3 is something, 18, that's too much for my brain, so 288. And distributing the 16, we're going to get negative 144 minus 96h minus 16h squared, and I'm just going to 288 plus 112 is what, 400. And now I'm going to just clean this up a little bit more, right? So 400 minus 144 gives us 256. Negative 96 and a positive 96, that's nice, they're going to cancel. I cleaned those up already, so minus 16h squared. Okay, so that's my h of 3 plus h. Remember, too, I should have said it earlier, but we're looking for the velocity at t equals to 3. That means we're looking for the instantaneous rate of change, the slope of the tangent line, of the function h at the point where t is equal to 3, right? What is h of 3? Well, h of 3 I know just from the graph is 0, right? If I plug a 3 in here, I could do that. I would get 0. So h of 3, no, it's not 0. Sorry. Hang on. Let me just make sure. Yeah, I was wrong. It's 256. Okay? So, popping these two things, so this is my h of 3. So now, rewriting the formula, the limit as h approaches 0 of 256 minus 16h squared minus h of 3, which is 256, all over h. The 256's are going to cancel. If I factor out the h, I have negative 16h over h. Those h's will cancel. So now I can take the limit, and bingo, it's 0. So the derivative is 0. Okay, and I just showed you why. But you can clearly see why without doing any work, that the slope of the tangent line is 0. So keep that in mind at that point. And then finally in part D, so I'm going to work up here, D, we want to estimate to the nearest hundredth the velocity of the ball the instant it hits the ground. Now, I heard a lot of chatter, so even though I was teaching those who were new to the class or needed a little bit of extra help, I could hear what was going on in the background. And a couple of you said or made the statement that, well, once it hits the ground, the velocity is 0. No, it's not. And the velocity is not 0 when the ball hits the ground. So the ball, when it actually hits the ground, has some velocity to it. So what are we going to do? Well, I know the ball hits the ground at some time. In fact, I know it's at t equals to 7, or I think it is anyway. Why do I think that? Well, if I take this function, so before we actually get into d, it's labeled d here. If I factor out a negative 16, I'm left with t squared I'm left with t squared minus 6. Oops. See, I have to use my calculator because minus 7. Yeah. T minus 7. It's a quadratic function. And I noticed that everything here was divisible by negative 16, so I pulled the negative 16 out. So really what we need to focus on is this little trinomial here. That's easily factorable, right? 2 minus 7 plus 1, right? Time cannot be negative, so if I solve each one of these factors, I'm going to get t equals to negative 1, so I can discard that one right away. That's irrelevant. Here, though, t is equal to 7. What does this mean? This means these are the zeros of the function, or the place, this damn thing, the place on the x-axis where the graph crosses, right? The zeros of this function. So, at 0 it's 112, so this is t equals to 7 over here. Now remember, when the ball hits the ground, it's going to bounce, so it's going to keep going until it finally stops somewhere miles down the road. But anyway, this time value here is 7. So is the x-intercept, one of the x-intercepts in a parabola. And in this case, the only one, since the other value was negative. Okay, so anyway, what I know is that the ball hits the ground at time equals to 7. And the problem is I've got to estimate to the nearest hundred the velocity of the ball. Well, that's an endpoint in your mind, right? I mean, we don't care what happens to the ball after. The last part of our question is what's the velocity when it hits the ground. So in our minds, this is our endpoint. And we can't do anything with an endpoint, right? They're special. So remember I said that the best we can do if we're trying to estimate a velocity at an endpoint is find a point to the left or the right. So in this case it'd have to be to the left, right? Because there's nothing past here in our world for this problem. Get a point really, really, really close to that endpoint and use that to compute the slope of a secant line, which will give us a really good estimate of the tangent line or velocity. So how about t equals 6.999 to t equals 7. The average velocity in this case is going to be h of 7 minus h of 6.999 all over 7 minus 6.999. Well, h of 7 is 0, right? I mean, we can see that, but we could plug the 7 into the function too and see it as well. Now, 6.999, negative 16 times 6.999 squared plus 96 times 6.999 plus 112 is 0.12798. I'm just going to bring it out so I don't make a rounding error, over 0.999, right? 7 minus 6.999. And if I divide that negative 0.12798 by 0.999, I'm an idiot this morning. Sorry about that. Miss Wilson can't add or subtract. I can do calculus, but I can't do arithmetic. Alright, sorry about that. All this means as move my decimal up here 3 places, right? So what I end up with is 127.9, so I'm going to call it 128 negative feet per second. And guess what? That's what it says on the answer key. So the best I can do is get really, really close to the end point from either the left or the right, depending on, what my situation is. In this case, I had to come in from the left, choose a point really, really close to the end point, and use those 2 points to compute the slope of a little tiny secant line, which should be the same as the slope of the tangent line, or at least give us a really good approximation of the instantaneous velocity, or velocity, same thing, at that point. Okay, so the ball does have velocity, and it's negative 128 feet per second. Now, using the calculator, let me put this thing in here really quick. Okay, so I put the function in the calculator, and I'm going to hit the graph key. There it is. Now, this is an axis, I think. Maybe not. I don't even know what my window's on. Anyway, you could do a zoom fit if you wanted to. My window was weird, so it's kind of weird that it popped up like that, but my window was weird because I was doing something weird later last night on it, so I didn't change my window. But anyway, I can see the top of this thing, so that's all that matters. You want to see the max or the min of your parabola. Okay? So in part A, when we wanted to find the maximum height that the ball attained, all you have to do is second, calc, maximum, 4. You go a little to the left of the bump and press enter. Go a little bit to the right of the bump and press enter, and press enter one more time. And you see the maximum height is 256. Look at this. The time at which it reaches that is 3. We wouldn't say the time is 2.999, we'd round that to 3. Okay, so part A not only gives you the maximum height, it tells you at what time it attains that maximum height. In part B, we calculated the average velocity from 0 to 7 because that's what it asked us to do. If you look at your table, at 0, it makes sense, right? If we plug a 0 in, the height's 112. The height's 112 before we even toss the ball. But look what happens at 7. It's an intercept, just like we showed. So, you can use your table, you can use your trace key, or in this case you can count because it's right on there. That's your intercept. So in part B, anyway, it doesn't give me my average velocity at negative 16 feet per second, but it does show me that 0 and 7 are clear, well 7 anyway, is clearly an intercept for the graph. In part C, they wanted the velocity at t is equal to 3. Well, on the calculator, you can clearly see that the slope of the tangent line there is horizontal, so it's 0. But you could do second, draw, tangent at 3, and hit enter, and there's your horizontal tangent line, and you see that the slope there is 0. Okay? So that gives you your velocity at t is equal to 3. And then in part D, guess what? You want to find the velocity at 7. You could do second, draw, tangent at x is equal to 7, and hit enter, and it's going to draw that tangent line, and your slope is 128. So the calculator can do a lot of work for you very quickly, but this really wasn't so bad. It took me some time because I was explaining things and whatnot, and correcting mistakes that I made, but still really not that bad overall. Alright, number 8, I'm just going to use this graph. So number 8, they're asking you some questions about this function, this graph. When is the car moving the fastest? We know the car is going to move the fastest where the slope of our function is the steepest. So I would say on the interval from 0 to t sub 3, it'd be here at t sub 2. That would have the steepest slope there. is the car speeding up or slowing down in the interval t sub 1? So over this interval, is it speeding up or slowing down? It's speeding up. And how do I know? You know, if I think of this little tangent line slope, the slopes of the tangent lines are getting steeper. So that means that the vehicle or the car is speeding up. And from t sub 2 to t sub 3, is the car speeding up or slowing down? Well, it's clearly slowing down. This is the steepest slope, and this one's a little less steep, and this one's a little less steep. So it's headed towards 0. Also, furthermore, this graph kind of goes from somewhat concave up to concave down right about t sub 2, right? And so, what was my point? Yeah, concave up to concave up, we know that the tangent lines are going to be increasing. Concave down, we know that the tangent lines are going to be decreasing. So just try and keep that in mind. And I explained the answer, so we're done with number 8. Number 9, we're given a derivative. We want to sketch this thing on the calculator and use it to answer the following question. So let me put that in my calculator. So x cubed minus 3x plus 1. Graph. Oops, gotta change my window, hang on. I'm going to do a zoom 6, and there's the graph. Now don't forget, this is the graph of the derivative, right? So in part A, it says, at what x coordinates on the graph will the tangent lines be horizontal? Well, you might say 1 and negative 1 and 1, but you better be careful with that, okay? You better be careful. So, I don't know, is that the answer? I just want to see. Yeah, the answers are these weird little decimals. So, again, to me it looks like at negative 1 and positive 1, but I could be wrong. Oh, I could be thinking of the wrong graph, right? Better make sure I know what I'm talking about. So, this is the graph of the derivative. And a lot of kids will look at this and say, oh, there's a bump here and a bump there, and so that's where my tangent line is going to be horizontal. Wrong. Okay, so I was showing you how you could be led down the golden path. It's not true. If this is the derivative, and I'm trying to figure out where the tangent lines are going to be horizontal on the graph of f, I need to find the zeros of the derivative. Okay? Well, there's 3 zeros on this derivative. And they're not at negative 2 and I don't know what that number is and 1.5. We need to make sure. So to do that, you're going to use second calc the zero function, number 2. And for the first 0, you need to go a little to the left and press enter of that 0, and a little to the right of that 0, press enter. And press enter one more time, and you can see we're going to have a horizontal tangent line on the graph of f when x is negative 1.879. I need to do it again for the next 0. Second calc 2. I'm going to toggle over here a little to the left of that 0, go a little to the right of that 0, enter one more time, and clearly that 0 there, we would expect a horizontal tangent line on the graph of f at x equals 0.3473-ish. And one more time, second calc 0, I'm going to go over to the left, enter, to the right, enter, enter one more time, and we're going to have another horizontal tangent line on the graph of f at 1.532. This is the graph of f prime. Don't forget that. In part B, suppose you were told that f of negative 1 equals to 5. Write the equation of a tangent line when x is negative 1. Okay. So I need scratch paper now. Jeez. Here's some. Okay, I know my derivative, f prime, is x cubed minus 3x plus 1. I know that f of negative 1 is equal to 5, and I want the equation of a tangent line at x equals to negative 1. So in order to do that, here we go again. Please just stay focused. In order to do that, since I have the derivative function, I can find the slope of the line really easily. f prime of -1 is equal to -1 plus 3 plus 1, or 3. So I know the slope of my tangent line is 3. I also have the point -1, 5 on the function f. If I plug in a 1, I get a 5. Since I have a point and a slope. Oh my gosh, this thing is going to drive me crazy. Sorry about that. I don't know what it's doing. I can use point slope formula and plug everything in. So y minus 5 is equal to 3 times x minus a minus 1. Done. You can leave your equations just like that. Unless they're simplified on your test, you know, because some of it's going to be multiple choice, so a lot of times AP will simplify. Sometimes they do, sometimes they don't. So, and that's it for number 9. Pretty cool little problem. And number 10, that's a big pain in the butt just because there's lots of decimals and I'm over decimals. But let me put this function g of x in my calculator. So we've got the absolute value function, by the way, because some kids ask me, if you want to put the absolute value symbols in, it's just math, right arrow, and you see number 1 is ABS. So it's math, right arrow 1, and there's your absolute value bars. But anyway, this is x to the 4th minus 16, right? And I'm going to hit the graph key. So I'm probably not going to see the graph. Oh, I did. So I don't see what I want to see though. So this is going to be like parabolic in between. So I'm going to go to my window and I'm going to go y max to 25 and hit enter. That way I have a good, there we go. Oh, look at that, W for Wilson. Okay, anyway, we have a good look at all the features, the important features of the graph. So there's our function. It says, what can you say about g prime of 4? Well, meaning, what is the derivative when x is equal to 4? I don't know, but I can do second draw tangent at x equals to 4 and hit enter. And I can say, oh, it's 256. G prime of 4 is 256. Super steep slope. Right? What about G prime of 2? Okay, I'm going to clear the drawing. So second draw 1 clears that tangent line. Otherwise it's going to stay there. I don't mind it being there, but some of y'all might, so. Alright, so G prime of 2. So second draw tangent at x equals to 2. Enter. Huh. What does that mean? Well, guess what? These are cusps here. So I want you to be really careful. I want you to see what the calculator does. Just sort of draws a straight line at 0. That means that the answer is 0. It's drawing a tangent line here. Or I don't want you to think that it means the answer is 0. Those are cusps. If I zoom in at 2, so trace 2 equals, and then zoom in a couple of times. The reason why I say this is it truly a cusp? And zoom in again. Yeah, it is. It's a point. It's a corner, and it's not gonna smooth out or get curvy or anything like that. The derivative does not exist there. So we'd say at g prime of 2, the derivative does not exist. Back to a zoom 6, and then g prime of 0. So remember, I had to fix my window there a little while ago, and I went up to 25 in the y direction so I could see what's going on up there. And at 0, that's a horizontal tangent, so definitely the tangent line is 0, or the slope of the tangent line is 0 there. Okay, now if we change this function, so to put a 4th root in your calculator, you press the index number. So just to flash back to Algebra 1, the little number here is called an index, right? When there's no number there, it means the square root, so the index would be 2. But all other indices will have a number. So if you want to put anything higher than a cube root in your calculator, you press the index first, and then you press math, and then number 5. You see the little X there? And see how the calculator will put the 4th root? So we want the 4th root of x minus 1 to the 4th plus point, how many zeros? 1, 2, 3, 4, 5, 1, 6. And I'm going to hit graph key. And so it says find all values for which the derivative does not exist. So you might be saying, right here, I got an issue, right? There's a corner. Well, you better be careful. So I'm going to just trace around 1, and I'm going to zoom in. I want to investigate, is it really a corner, or is it not? So you're going to want to zoom a couple of times. It looks like a corner to me. I'm going to zoom in one more time. And that's not a corner. Let me zoom in one more time. Ooh, look at that. That is not a sharp corner. So, initially speaking, depending on what your windows are, chances it's going to default to a Zoom 4 or Zoom 6 viewing window. That's going to look like a sharp corner. And I urge you that every time you graph something on that calculator that looks like there's a sharp corner in it, you trace to that value or around that value, and you keep zooming in, 2-3 times, just to make sure, because sometimes first looks are deceiving, and that is not a corner. So I would say that the derivative exists everywhere on this function. Okay, but a lot of kids, they'll just, graph it, they'll put it in, they'll get this initial graph, and they'll say, oh, the derivative exists everywhere except for x equals to 1, because man, does that look like the absolute value function, right? It sure does, but it's not. So don't be deceived. Conquer the AP trickery. Okay, finally, number 11. So number 11 says, suppose f of 2 equals 3, and that f prime of 2 equals 4. Write the equation of a tangent line at x equals 2. Well, guess what? You have the slope of the tangent line. That's 4. You have a point, so y minus 3 equals to 4 times x minus 2. Fini. Done. That was part A. Part B, suppose f of x equals x squared, then f prime of x equals 2x. Write the equation of a tangent line at x equals 3. Okay, well I need a point, so I'm going to plug 3 into f and get 9. So I have the point 3, 9. I need the slope of the tangent line. Well, I've got the derivative, so f prime of 3 is equal to 6. So I have the slope of 6, so y minus 9 is equal to 6 times x minus 3. Done. And in part C, it says, suppose the function 2e to the 3x is given. Find an equation of the tangent line at x equals to 0. And they say, hint, use, and deriv. Okay, so you don't have the derivative here, so for something like this, you'd have to use your calculator. Hang on, baby. Ella here, my dog, wants to go for her morning walk. Oh, you want to go for a walk? We're going to go in just a minute. We're going to go in just a minute. So we have 2e to the 3x. Okay, so I put that into my calculator, and I'm going to hit the graph key. And it's going to look like e to the x, right? But with a little bit of modification, a little bit of stretch and whatnot. Find the equation for the tangent line to f at x equals to 0. I'm not using n deriv for that. I'm using second, draw tangent at x equals to 0 because I think it's faster. And bam! The slope is 6. And not only is the slope 6, but the equation is y equals to 6x plus 2. By the way, I understand that when your calculator does this kind of work, you get, a 9-digit slope. Okay, you're not going to write out all 9 digits times x plus or minus whatever the constant is, okay? Just round it to 3 places past the decimal if it's really decimally, like, not a bunch of zeros. Or round it to the nearest whole number, okay? I don't want to see on a test that y is equal to 6.20 zeros. Well, alright, so there's 9 digits, but anyway, 5 zeros, a 9, 3 more zeros. Don't do that, okay? Round it to the nearest whole number, or to 3 places past the decimal if there's not a whole lot of zeros in that decimal. And that concludes page 2.